Hello Chem 1A, this is Chapter 6, Lecture Video 6, and we're going to be talking about the first law of thermodynamics. There are actually a number of different laws of thermodynamics. This is really the only one we cover other than the law of conservation of energy, which we already talked about. There's also the second law of thermodynamics. This gets covered in Chem 1B when we revisit thermodynamics. And so what the first law of thermodynamics, in part of it is the law of conservation of energy, that energy can neither be created nor destroyed, it's conserved. And we transfer energy just straight up between our system, our investigated thing that we're looking at, the process we're interested in learning about, and the surroundings. Internal energy is also part of the first law of thermodynamics. And internal energy is effectively all the energy within a substance. So it's kinetic energy, Ke for kinetic energy, and its potential energy, right? Remember we learned about these earlier in the class. So the internal energy is always equal to the kinetic energy in our substance plus its potential energy. Now we usually use U or E, however, E is becoming more often used for the symbol of internal energy. We can't actually measure how much energy is present in an object, period. We can only measure how much energy leaves or enters an object. We can measure changes in energy, but not energy directly. So generally, we actually are measuring delta E or delta U. Again, these two symbols are interchangeable. They both mean internal energy. And so delta E would be E final minus E initial, or U final minus U initial. It doesn't really matter. At the end of the day, we can't actually calculate it this way because U final, U initial, we can't measure those because they're the amounts that the object has right away. We can only measure the change in the energy, which we calculate by using Q and W. Q is heat. We've talked about it quite a bit in the last couple lecture videos. And we can calculate Q using Q is equal to MC delta T, or Q is equal to mass times the delta H of fusion, vaporization, what have you. What's W then? W is a measure of work. And so how do we calculate how much work is being done by our system? That can be done using an equation that we'll learn on the next slide. So, work. Work can be done on the surroundings by the system. In other words, the system is doing the work. In this case, W for the system would be negative. Nobody likes doing work, neither does the system. We're losing energy because the system is doing the work. Work can also be positive though. If the surroundings is doing the work on the system, the surroundings is doing the work, the system's getting work done for it. That's a positive thing for the system. Work for the system is going to be positive in this scenario. How do we calculate these values? We use an equation, negative P, which is pressure, times delta V, which is change in volume. This has to be calculated in liters. So in other words, our delta V is equal to our volume final minus our volume initial, and both these values need to be in liters when we do this calculation. And the reason for that is because of a conversion factor we use with this equation, which is that 1 atm times liter is equal to 101.3 joules. Now this equation spits out values in atmospheres times liters, and we want to calculate joules so that we can use it with heat in the previous equation for internal energy. I will always give you this conversion factor in the problem, so don't worry about it, memorizing it. Now, change in volume can happen in a number of ways, right? Against an external pressure, that's what the P is here. So in this case, we put some dry ice, right, here on this spoon into this Ziploc bag, and dry ice does something cool. It sublimes. It goes directly from the solid state to the gaseous state. And what it does is it eventually does all of that. It changes directly to a gas, and it inflates our Ziploc baggie. And I guess in this case, we're going to use the Ziploc baggie to do work and hold up our book, because, you know, that's something we do. But nonetheless, it is doing work. It's inflating that Ziploc bag against the pressure of the room, whatever the pressure is out here, right, outside the bag. It had to press against that and do work to do that. So the sign of delta E or delta U, internal energy, change in internal energy, can be either positive or negative depending on what's happening in the system. For instance, if heat is transferred from the surroundings to the system, then we know the system gained energy, so Q is going to be positive. Work done on the system by the surroundings is positive because the system's not doing the work, so work is positive. In this scenario, if we had Q being positive and W being positive, remember this is equal to Q plus W, so delta E or delta U is going to be positive too. At the end of the day, you can kind of figure it out from the wording there, but if the two are opposite sign, then we need to do the calculation and determine the value. Okay, so in this case, like I said, in this case the system is positive. Let's do an example problem, right? So we have our equation is our internal energy or change in internal energy is equal to Q plus W. And we're actually told what Q is in this problem, right? We're told that the system releases 47.8 kilojoules of heat. That means Q is equal to negative 47.8 kilojoules of energy. And we know it's negative because of the word releases. If it's releasing it, then the system lost the heat, meaning Q would be negative. We also know that work is equal to negative pressure times delta V. And so we have the pressure given, it's 35.6 ATMs, and that's negative, times our delta V, final minus initial, so 0.476 liters minus 19.4 liters. This gives me a W of 673.7. And this is in atmospheres times liters. Now, before I can add these two together, I need them in the same unit. So I need to take my 673.7 atmospheres times liters and go, hey, I know that according to this relationship here, 1 ATM times liter is equal to 101.3 joules. I then want to convert to kilojoules because this guy's in kilojoules. So I know there are 1,000 joules in 1 kilojoule, and this is going to give me 68.2 kilojoules of energy, and it's positive because the equation spit out a positive value. So delta E then, our internal energy, is equal to negative 47.8, our Q, kilojoules of energy, plus positive 68.2 kilojoules of energy, and this is going to be equal to 20.4 kilojoules is our delta E. All right, so if you have any questions, as always, please feel free to contact me in my office hours or via email.